Ratiu. With great pleasure, I introduce him, and I would make only two remarks because Tudor is the director of the Bernoulli Center in Lausanne, and Bernoulli was one of the first person who came to Russia during Peter Grade's governor to try to help Russia to be a famous or great scientific country. And Tudor decided to repeat this adventure recently because he had what it's called Russian mega grants. He is a very adventurous person because all others head of these grants, they are former Russians. But Tudor, he did not know Russian, now only he studied Russian. And so he has very small or little experience with Russian reality because he was from Romania. But Romania it's difficult to say that Romania is small Russia. It's something, there are some similarity of Soviet period, but not so. So if he survives, so I wish him, and because he invited me to be the member of this grant, I wish him success in this very, very adventurous activity. So his talk is in this direction.
Thank you very much. Quite an introduction. Thanks a lot. So, what I would like to talk to you about is something that several of us have been looking at on and off, and we are trying to understand this from a variational point of view and also from a Hamiltonian point of view. So it's a series of two papers. Of course, I cannot possibly tell you what is in both of them because they're quite large, they're quite big papers. If you want to take notes, don't. I just give you the transparencies. I don't mind. I just want to give you an idea what's going on. So I have to give credit to my collaborators. It's François Gebalma, the CNRS at the École Normale, Daryl Holm at Imperial, and Vakhtang Putkaradze. But in fact, Vakhtang right now also has a third position in Edmonton as we speak. Okay, so this is quite a group of people. I mean, Vakhtang is a physicist turned mathematician, sort of quasi-engineer. Daryl Holm is a physicist turned mathematician. He's in the math department at Imperial. And François was my former student, but he's in the department of, how do they call it, dynamic meteorology or something like that at the ENS. Okay. So the plan is very simple. I would like to talk about dynamics of molecular charge strands. Everything will be conservative. There are no dissipative terms, which of course can be criticized, and I have to put them later in. Then I want to show you the mathematics behind it, which has to do with affine variational principles and also the Hamiltonian counterpart. And then, time permitting, I'm going to show you what happens if you have multi-bouquet. I'm going to do two of them, but if you want formulas for n, I can give them also, but not here. Okay, so what am I dealing with? So I'm dealing with the long molecules, and I think of them as strands of charged units. So the dynamics depends both on the local elastic deformation and on the non-local, the screened electrostatic interactions of the charged units across the folds of the molecule. The electrostatic interaction depend on spatial distances and relative orientations between the fluid charges. There have been attempts to do this. We are by no means the first ones. I mean, don't get me wrong. This is a very, very old, time-honored subject. The full dynamical simulations are complicated, and I'm certainly not a numerician. I don't know how to do this. And this was part of the motivation. We try to understand it in principle, what's going on. The continuum approaches go all the way back to Kirchhoff, with the remarkable paper. I will comment on Kirchhoff's approach. I will not present it here. It's in the paper, and I can tell you various things about it, if need be. So, if you want to generalize the Kirchhoff theory to account for the torque caused by the long-range electrostatic interaction of molecules, then you have to deal with it at different spatial locations. These things fold, right? So the problem, our problem, from the point of view sort of a classical continuum mechanics, is that Kirchhoff deals with a mixture of variables. He's neither material nor spatial, not convective. maybe I should make some comments on this. I mean, for me, when I do continuum mechanics, if I don't understand it three ways, I don't understand it. There is the material representation in which I am a particle and I write the equations of motion. There is the spatial or Eulerian representation, the previous one is also called Lagrangian, in which I am on the shore and watch the fluid flow, or I am here and watch the body get deformed, right? And then there is a convective in which I am in the body, fixed to a frame, and the body is moving and deforming, but I'm moving with it. And this has consequences in the mathematics, and it's quite interesting. Okay, so there are various problems. I put them here. I'm not sure I should go through all of them. The curve can cross itself. There are problems that are non-local. How do you deal with this? Kirchhoff certainly could not deal with these problems. Okay, this is just stories. This is what I'm talking about. So I'm talking about some elastic filament, and these guys here are rigid, right? So there are some charges here, that's how I imagine them, and these are fixed, these are rigid, but this is moving, and but they can rotate. But these rods here cannot be deformed. So this is what we call rigid charge conformations. They're mounted along a flexible filament, and I want to use exact rod theory to do this, and I want to use convective representation as people do in elasticity. I can comment on this further, why convective and not spatial, but that's just let me do it in the convective representation. It has advantages. So there are such situations. For example, here is a specific chemical compound that looks exactly like this. Now, the theory, by the time I'm done with it, will generalize to other things. You don't have to be on a filament. You can be on a two-dimensional manifold, on an n-dimensional manifold. It doesn't matter anymore. You will see. So I start with the material or Lagrangian representation. So what do I have? I have some matrices, rotation matrices, proper rotation matrices, that depend on the position, which is S, and on time, which is T. And I have the vector position, exactly as in my picture, the R of S and of T. And these lambdas are moving these charges around. So RST is the spatial position of the filament, and the variable lambda ST denotes the rotation of the RCC at this point. And then what do? I compute the velocities. These are the time derivatives are with dots. The space derivatives are called prime. Okay, so now I'm going to introduce various objects that I need to introduce. And you already start seeing my sort of my Lie algebra predilection, the way I write things down. So I have a lambda prime or a lambda dot, right? So if lambda is in the group, if I take some kind of a derivative, I'm going to be on a tangent space somewhere, right? Well, I bring it back to the identity, and I bring it back left, not right. I bring it by left translation back. This is by all the lambda minus 1s are on the left. Now, this is going to be a skew-symmetric matrix, and I represent it as a vector. So these bold-faced guys, these are just vectors in R3. So the isomorphism between R3 and SO3 is simply given by the cross product, or if you want coordinates, is very easy. To the vector which has coordinates V1, V2, and V3, you associate the matrix that has 0, minus V3, plus V2, minus V1, and then make it skew-symmetric. And this takes the bracket operation, the commutator, into the cross product. It has an annoying minus 1/2 in terms of the killing form, but we can deal with this. And then there are things that I do also to the position. There is a prime, a space variable, and a time variable. And I do the same kind of translation by the same kind of rotation by lambda. And of course, I'm not going to write lambda minus 1 lambda because this is stupid, it's just the identity. However, lambda minus 1 r means something, right? This is the position. So the physical interpretation of the variables are the following. This rho represents the position of the filament in space as viewed by an observer who moves with the RCC at ST. This is the convective representation. The variables omega and gamma describe the deformation gradients as they speak in elasticity theory as viewed by an observer who moves with the RCC. Those of you who do manifolds, this is the tangent map, right? And they call them deformation gradients. There's no gradient involved here, of course. And the variables omega and gamma describe the body angular velocity and the linear velocity viewed by an observer who moves with the RCC. Okay, so here are my variables, lambda, r, omega, gamma, and rho. And these are functions of S and T. Now, you can see these things in two ways, and they give rise to two theories. I'll present you only one. If you are interested, I can give you also the other one. There is sort of a classical mechanic approach, if you want, and the field theoretical approach. So, both of them are very useful. So, you can interpret lambda of ST as a function of space and time. Or you can see lambda as a curve in the infinite dimensional group, right, of functions from 0L, which is the length of the strand, into SO3. Now, it's important. One of them gives you, which I will present to you, the Euler-Poincaré. This is sort of much closer to classical mechanics. And the other one gives you a covariant point of view, which we call the Lagrange-Poincaré approaches. Both of them are done, but there is no way I can show them to you both here. So the second approach I will not discuss in this talk. Okay, so I want to get going. So what is the energy? Well, I have a curve. This is my filament. I have a spatial reference, the undisturbed state of the case charge, and I write it as R of S plus this rod, eta k, right? It's just that fixed rod. So these are given to me, these eta k's. Eta k is a vector of constant length that determines the position of the case electrical charge relative to the point Rs along the curve in its reference configuration. And this eta k specifies the shape of the rigid conformation of charges. What happens at time t? Well, at time t, the position of the vector will move, and there will have some rotation, right? Of course, this doesn't depend on t. This is given, this eta k. This is fixed at any s in the on the filament. The first person who has done such things in this modern language is Igor Mesic in the proceeding of the National Academy of Sciences. He did this for SO2 and k equal to 1. It's a very nice paper. So let's start looking what is involved here. I have a vector of a charge k. Let's call the charges k, m, n, whatever the terminology, the numerology is there. And I have another one, another charge m at the point S prime. So then the potential energy will depend on the distance between them. So I look at the distance between S and S prime. So then I compute, right? I just plug in everything. After I plug in everything, two new objects appear. One of them is lambda minus 1, the difference between, at the point S, the difference between Rs prime and S, and psi of S prime, which is lambda minus 1 of S, lambda of S prime, right? So these are sort of group theoretical objects, and this is a representation, this is a representation theoretical object, right? SO3 is represented on R3. So here is the same picture, right? So that we know from whatever literature is out there that the potential energy depends on this. So here is the first observation. If you look at these objects, at my psi and at my k, this is simply, you take the Euclidean group, which is the semi-direct product of SO3 with R3, right? It's just rotations and translations. And these objects are literally nothing else than lambda r minus 1 with lambda r at two different points. So it's a group theoretical affair that I'm seeing.
Could we just go back one slide? Your definition is kappa the curvature, or
no.
That's why I'm getting confused.
No, I'm running out of letters.
Okay.
Right, I'm trying to keep Greek letters for certain things and Latin letter for other things and so on. No, it's not curvature. It's literally that.
It's like a chord. It's like a chord on the on the curve.
It's a distance, and then you rotate it.
Okay. All right.
Okay. Now the energy appears in the literature. It has two parts, and of course, one of them is going to be much easier than the other one to deal with. There is something that is local, and this local part of the energy depends on omega, gamma, and rho. And there is a non-local part. And this non-local part appears in the potential energy, of course, and is determined by some interaction potential. Leonard-Jones, for example, right? For me, it's just some interaction potential. And it looks like this. But if you look like it this way, you can multiply by lambda minus 1 here, and lo and behold, you get your gamma and your gamma prime, your gamma and your gamma s prime. And then the Lagrangian is going to have a local part, which depends on omega, gamma, capital omega, capital gamma. Remember, these are translated back to the identity, time derivatives and space derivatives, right? And some non-local part. And this, so the energy is going to be some kinetic energy, the obvious one, minus the local part, for example. And the to which you have to add the non-local part. And the non-local part, well, it looks like this. We are going to actually go slightly more general because it's no big deal. Just some function that depends on psi and on kappa, on gamma and on gamma at s prime. Double integral of this. See, here is an example of such a thing. Right? Okay. So what is the filament dynamics? Now let me give you a very dirty and quick derivation of the equations of motion. And then I have to step back and say, what have I done? So what am I doing? The idea is I'm going to use the Pontryagin principle from control theory. Some version of it. The idea is to introduce Lagrange multipliers. And if I do this, I'm going to get some equations out of a variational principle. So let's try to do this, right? No questions asked at this point. So I'm taking my Lagrangian, and you see here are my Lagrange multipliers, little pi, capital R, mu, and m, right? Because I want these things to be true. Lambda minus lambda dot, I want it to be omega. You have seen the definition. I want this to be capital omega, etc., right? So these are the constraints. So I'm going to set delta s equal to 0, and let's get going and see what I get. So what I get is all these relations, right? But of course, for example, if I have a pi, here is a pi dot, I take my delta L, delta omega, and plug it in here, right? I mean, I really have something. And then I have my constraints, right? Of course, if I want to set delta pi equal to 0, I'm going to get back exactly what I wanted. Sure, that's how I built it, right? What else could I possibly get? What do I do about the non-local terms? Well, that's a bit more annoying, but I can do it also. So here is my non-local part, right? Here it is, written out. And now I put the other Lagrange multipliers, right? The x goes with the psi, right? I try to keep some kind of a discipline in my notation. And then I get who are the Lagrange multiplier, and I get some equations here. Gamma cross m is this, and m prime, there's the space derivative, is equal to this. Now I have to plug everything back. Now you sit down and compute, and you compute a little bit. It's not something that you can do in your head. There is a certain quantity that appears here. This is z hat. That has to do with the potential. And by the time the dust settles, 3-4 pages later, but it's, it's not here, it's here. It's muscle, right? You get the equations of motion, and here they are. So dt plus omega cross of this, here they are, right? One equation, the second equation, and then quote-unquote advection equation, like mass conservation, etc. They're not quite like this because they have a right-hand side, right? It's not dt rho equal to plus rho omega equal to 0. It's not. There is a gamma. But okay, no problem, right? And also with the space, time and space variables appear in both of them. Now in the Kirchhoff filament, rho and psi are absent. So they simplify enormously these equations. Now, in addition to that, if you want to use non-holonomic constraints, you can do this also. It's no big philosophy. Okay, so far so good. I got something. It's getting more interesting if you go one more step further. Well, you can say, I have these constraints, and let me compute the variations of these constraints. So I compute the variation of these constraints. I compute for rho, for omega, for capital omega, for kappa, for everybody, right? So here they are. They are explicitly written down. And then my Lagrangian, I can look at my Lagrangian, the local part and the non-local part, here it is, and I apply the variational principle with these constraints. No questions asked. I'm not justifying it yet. Just do it, right? You get the same equations. So what have I done, right? That's my question. I want to answer geometrically, what have I done, right? It's clearly right. I get the same equation in two ways. One of them by some kind of a Lagrange, obvious Lagrange multiplier machine. The second one by something that we are quite familiar with from Euler-Poincaré theory, which I will review for you very quickly. There you have constraint variational principles. And I computed the constraint variation absolutely by the seat of my pants. I just solved it, and I just took the derivative, right? Okay, so now I have to step back and do a little bit of theory, right? And it's amazing what is involved here. It's, the mathematics that's involved is quite sophisticated. And that was quite a surprise. So the first thing is we are going into the realm of pure algebra now. Of all things having to do with one cocycles in group cohomology, right? So here they are, but I tell you what they are in a humane way. I also have trouble with this very abstract algebra, trust me. So I have a left representation on some vector space. In fact, it's not the vector space that I'm interested in, it's the dual of the vector space. So I have a representation, take the contragradient representation or the induced representation on the dual, so I have it. So I can form an affine left representation. Here is the action of G on somebody in V star, and I add something to it. Now I want this to be an action, right? So I write theta E of A has to be the identity, and I have to write theta G1, G2 is theta G1, theta G2. Obviously, this is going to impose some relation on G, right? That relation on G is going to be this one. CGA is equal to CG plus G times C of H. This is one of the forms of the definition of a group 1 cocycle. Okay. And then, of course, I have the infinitesimal generators. I write it here. I have, I reminded you of my sign conventions, what my sign conventions are when I act on the dual. When I mean contragradient, if I'm left, I don't just take the dual, I take the dual minus 1, because I want to stay left. So that introduces various minus signs, relative minus signs, so I have to be careful with this. And I have to tell you what is this transpose, the obvious thing. There is only one operation which is odd, which is called the so-called diamond operation. If you're a symplectic geometer, this is just the momentum map. But forget it, I'm not going to use that much sophistication, just purely algebraic in this case. It is, I give you an element in V, I give you an element in V star, and I produce an element in the dual of the Lie algebra that acts on it. So I have to feed to this xi, which is in G, and this is the pairing between, the natural pairing between G and G star, duality pairing. So this is a real number. What is that real number? That real number is, by definition, A with xi acting on V. That's it. Okay, so now I have some Lagrangian. My Lagrangian has a configuration space which happens to be a Lie group. And it has parameters. For example, in the rigid body, the heavy top, the parameters would be the strength of gravity, the length between from the origin to the center of mass, things like this. In fluids, in compressible fluids, this would be the initial density, the initial entropy, right? Or if you have in MHD, the initial magnetic field. So these are these parameters that float around with you. So I am assuming that it is left invariant under this affine G action. So I write it down explicitly. The formulas are not important for this talk. They're just important that they exist. I want to convince you that these are not theorems, there exists something. No, I can compute. So for any A, which I call it in the reference configuration in V star, the Lagrangian, if I freeze these parameters, then I have a classical Lagrangian on TG, right? And this turns out to be invariant under the isotropy group of the action relative to the cocycle C. So, for example, if C would be 0, I still would have a subgroup, right? Look here. See, there is a C here, there is a C here, there is everywhere a C. Right? If I would just take the contragradient representation, that G0 is 0, G0 is the whole group, right? Here it's not, because I have this affine action. Okay, it doesn't matter, it's some subgroup that I can specify. Okay, so now what do? I do the obvious thing. I can define a new function on the tangent space to the identity cross V star simply by restricting it, right? And because it was left invariant, once I know this guy, I know the other guy, just by extending it left invariant, right? Because that's the hypothesis. So information about capital L and little l is the same. But of course, there is an advantage. I lost lots of variables. Okay. So now, what is the problem? I give you a group curve, g of t, and I take its derivative, and I bring it back to the identity. Now I have a tangent vector at the identity, which is a Lie algebra element, right? I define a of t as the unique solution of an affine ODE with time-dependent coefficients. A dot equal to minus xi a minus dc of xi. I know the solution of this, no under quotation. Initial condition, let's assume it's g0 minus 1 and this, right? If I, whatever the initial condition is, I figure it out from the ARF because I know all the elements here. And the solution is given by the action. But of course, I don't know the action because I don't know xi, and g is the one whose dot is xi, right? Times g. So this is this is the phenomenon of advection, exactly like vorticity is advected, like mass is conserved, right? So I know it, quote unquote, if I would have known the other one. So here is a theorem in 4 points, which is a generalization of a theorem of Poincaré in 1901. So Poincaré in 1901 wrote an absolutely remarkable paper. It has less than 2 pages. He gives no references, he gives no motivation. He never worked on it before, never after. So I don't know, nobody knows why he did it. So what Poincaré has done there, and it's absolutely remarkable what he has done, he is worried about the rigid body, actually, but he's so general that, you know, it doesn't matter. He never uses that it's SO3. In fact, he works on abstract Lie groups. Literally, I mean, it takes nothing to go from SO3 to a general Lie group. So the question that he posed was, what variational principle gives the equations of motion that Euler has given? Pi dot equal to pi cross omega, like we teach in our class, in a mechanics class, right? And he's come to a conclusion. It is a constraint variational principle. And this is a generalization with parameters and with co-cycles. I need all this machinery. So here it is. These 4 statements are equivalent. With ARF fixed, Hamilton's variational principle holds, and G of t satisfies Euler Lagrange. Of course, no hypothesis. This we know, right? This we know since time immemorial. That's no news. That is known. That's classical mechanics. What is new is the Poincaré part that says that the constrained affine variational principle holds on G cross V star using variation of a certain kind only. So delta xi is equal to eta dot xi eta, and delta a is minus eta a minus dc of eta, where eta t is any curve vanishing at the endpoint. Okay, I'll come and comment on this. And because you have a variational principle, you should get the equations. So what equations do you get? The equations that you get are exactly these. ddt del L del xi is equal to add star xi. So for me, add star means simply turning the arrow around between the dual spaces. And add xi is take the bracket with xi. So it's a linear operator. I take its adjoint. So del L del xi, and then here I have this operation. Del L del A is a derivative. Variable is in V star. Therefore, this is going to be in V. Right? Here I jump a lot to function analysis, which sometimes I shouldn't do. And okay, it's formal at this point. Minus an affine term here. And this calls on G cross V star. So this I repeat for you again what this diamond operation is, so that you can see it here on the same slide. So what is the content of the theorem? I mean, let's try to pin it down. 1 and 2 are equivalent, that is classic, right? If I don't know 1 and 2 and I look at 3 and 4, it's extremely easy to prove that they're equivalent. What do? I blindly take the derivative. I get del L del xi, delta xi, plus del L del L, delta A. Now take my delta xi from here, put the delta A in there, integrate by parts in this term, and isolate the variable, eta. And you're done. What you get is this. This is the proof. It's literally no more than 6-7 lines of computation. Okay. So 3 is equivalent to 4. L is invariant under the group action, so obviously I can multiply here by g minus 1, and I'm not going to carry with me the identity, e g minus 1 g, but g minus 1 g dot is xi, so it's there, right? There is a slight trick here involved that the a ref turns into a. Okay, let me gloss over this, right? That is another little part. You have to argue about it, but you know, if you forget about the a, like Poincaré did in his time, then this is it. So this is obviously, this integral is the same as this integral. So what is new here? What is new here is this. Is delta xi is equal to eta dot xi eta, and delta is minus eta a plus minus dc eta. Let me explain this. When you do this variational principle, how do we teach our students? You take 2 points, you take a curve, you take a variation of the curve, and you take the derivative, right? Now, when I have a deformation parameter, I can also take the derivative relative to the deformation parameter. When I do this, I get another tangent vector to the group. I bring it back to the identity, I get a Lie algebra element, right? You've seen them explicitly when I wrote lambda minus 1 lambda prime, right? So I do this. So the question is, here I have all the variations as long as they vanish at the endpoints. But when I bring them back to the Lie algebra, do I have all the possible Lie algebra elements? The answer is no. What I get is precisely this. These are the delta xi's are only those for which you can find an eta that vanishes at the endpoint, such that delta xi is eta dot plus chi eta. It's not just all the delta xi's. This is where the content is. It's not difficult to prove, right? But it's not obvious. The rest was simple. Okay, so if I want to do Hamiltonian, I'm not going to do Hamiltonian because I'm not going to get anywhere. Okay, there is a Lipoisson thing here that is involved. Those of you who want Hamiltonian, I can show it to you. I just looked at the clock. Now, I want to apply this to my strand, but I have a problem. My problem is that my parameter is fixed, and I can't move it. In fact, I know only one single value of the parameter. See, this is in vast contrast with what happens in the heavy top or in fluids or in standard, for example, compressible flow, just rho, right? Sure, rho 0 is fixed, but I can choose any rho 0 I want, right? I can take all the possible densities rho 0 for the rigid body. I can take any length between the 0 and the fixed point. So I can consider all the families. Here I can't. I don't know what it is. I know it only at one single value. So this is a big problem because my theory obviously doesn't work, right? So it cannot apply like this, so I have to do something else. Now let's see what we have. So I have my Lagrangian, and this is given concretely for this reference configuration to be 0. And we do not know what L could be if it's off. And I don't want to guess because I don't know what I'm doing. Now I can extend this by the action because I want it to be invariant. But if I do this, I will not get everything. I get just the orbit through 0, and I keep putting this C up here to remind you that this has to do with the co-cycle. It's relative to the affine action, not to the representation. Okay. Now, fortunately, you check the Lagrangian of the molecular strand is invariant under this isotropy group. You actually can check this. We will see that this is enough for the extension of the affine semi-direct product reduction theorem. So there is another one. How do I do it? So I fix my ARF and assume that this one is invariant under this subgroup. But I will not assume, which was the case in the previous theorem, that this comes from a G-invariant function. No way. I cannot assume this, because it's not true. I don't know what it is. So to this LARF, I associate the reduced Lagrangian on the submanifold, the Lie algebra, and the orbit relative to the affine action, which is in G cross V star. So the orbit is the orbit, right? The group, I remind you, this is the affine action, which I call theta G, on this element. And this is given in the usual extension way, exactly as I did before. Now, the tangent space to the orbit is given. You take the derivative of the action, and there it is. The co-cycle comes in, and the contragradient representation is there. Now, I want to extend the theorem that I give to you in a different way. And it turns out that it works. So I have ARF in V star. I have my curve G of t. I have a G of 0 is the identity. I define my curve G minus 1 G dot. And I drag along my parameter by the action. And I have a similar theorem, which is formally identical to the previous one, but you have to do something. It's not trivial to prove, far from trivial. So again, Hamilton's principle holds, Euler-Lagrange equation, of course, it's classical mechanics. You have constraint variational principle, but not everywhere, only on G cross the orbit. Same constraints, and you have the same equations that are the Euler-Poincaré equations. Now, if the reference configuration is 0, then this group is just where the cocycle happens to be 0. This is the isotropy group, right? This is how you extend the Lagrangian from capital L to little l, and this is what you actually see in the literature. And then I have my little l, kinetic, and potential. Now, the right-hand side is well defined on the orbit, and it depends on G only through this. Even though, right, I shouldn't be able to write a G here, because I'm on the Lie algebra, there is no more group. So I have a problem. But you have to prove that this is true, even though you cannot say what the formula is. You can show that it is true, and I will show you in a second, you can take derivatives, in spite of the fact that you cannot write formulas. The derivatives, the formulas of the derivatives are explicit. So I have my potential is going to be a local part and a non-local part. So this local part explicitly depends on Cg minus 1, and the non-local part does not have a concrete expression only in terms of Cg minus 1, but it is invariant under this group. And K, actually the kinetic energy, that's easy, it's invariant under everything. So my situation is the following. I have some local part, kinetic minus potential, and a non-local part. And I write it this way and that way. So this zeta is a function that is invariant under this subgroup, and in terms of psi and A, I can write it down, but the problem is that I have to write here G index A and G depends on A, right? So that's not okay. But that's the best one can do. However, you can work in spite of this. So what is the setup for the strand that I showed you before? Now I give you all the objects. The group is going to be maps from the interval into the Euclidean group. The Lie algebra is going to be its obvious Lie algebra. The vector space is going to be, I write them as vector fields which are R3 valued, right? It's not vector fields, they're covariant contravariant one tensors. Vector value contravariant one tensors.
What's the difference between SE3 and SO3?
SO3 is just rotation.
Yeah.
And SE3 is rotation and translations.
Ah, okay.
Euclidean group. And S means determinant 1. Right? As opposed to like O3, SO3. And V star is the obvious duality, right? Vector fields go dual with one forms. So these are one forms with values in SO3. Okay. Now, who is the cocycle? The cocycle is explicitly written down here. Here is the expression. In fact, all I did is I copied what I have written on my slide number 3 or something like this. It turns out to be a cocycle. And then with this, I can compute this mysterious function zeta. And there it is. And the variables are lambda r are in G, right? Rotation, translation, right? Infinitesimal rotation, infinitesimal translation. And the guys who will get advected. Omega, capital gamma, capital rho. Okay? So, there is a technical problem here that, you know, if I'm going to start explaining, it's going to be a disaster. But, so forget it. It works. You have to take my word for it. If you look formally, it seems that you are missing a term. You don't miss the term. You have to be very careful, and there is an argument that shows that you don't miss the term, everything is fine. So, all of this that I told you has a formulation as conservation laws if you want them. You have Kelvin circulation theorem for this, or the analogs of thereof. You have a generalization that replaces 0L by a Riemannian manifold D, SO3 by any group O, and I put it O because I think of order parameter, like in complex fluids. and R3 by a general representation space of this order parameter group. There is also a covariant field theoretical formulation of all of this, which I haven't even discussed. And if you want, in this particular case, you can even form it in terms of quaternions. And certain computations become easier then. And there is a Hamiltonian formulation. Let me skip because I never get anywhere. Okay, so if I do the strand equations, I apply the theorem that I showed you before, blindly. I have this. All my hypotheses are verified. I understand what I'm doing. I came from a material representation. I went to a body or convective representation, right? And I have just proved the theorem that tells me that the fundamental Hamilton principle for mechanics is equivalent to this one. So instead of having material equations of motion, I'm going to have convective equations of motion, like we always have in elasticity. What are they? Here they are. And as you notice, they're exactly the ones that I had before. Of course, they actually look much better than I had before, because it organizes them. Remember, I had two horrendous ones, and here they are. If you plug, of course, L in what it is equal to with all this U and the local and non-local, it gets quite stuffy. But here you can see it, and you have advection type equations. Here they are. So we have assumed that the Lagrangian is given explicitly in D in terms of these variables. Okay. And if I have non-local terms, then I have to apply the other theorem. And there are various observations here that are important, that help. The non-local part is induced by an SO3 invariant potential. In fact, it's SO3 invariant. So the total energy can be seen as being induced by the SO3 invariant Lagrangian that depends on lambda dot r and r dot. And here it is explicitly written down. That's the kinetic part, the local part, and the non-local part. And K is usual energy. And you see here I even lost the interval. I just put any manifold. I don't care. The left invariant extension of the kinetic energy. So I have replaced the dependence on the local part of the energy on omega, gamma, and rho by dependence on lambda and r to the cocycle C. That is very useful sometimes. And the second one, SO3 is not just some SO3. This SO3 is precisely the isotropic group G0C in this case. So the thing that before that it was invariant was not an accident. It was exactly what I said in the theorem. You can compute it, and it's precisely this one, G0C, for which we need it. So then these remarks allow you to do it on orbits. You have to work a little bit more, and you can apply the other theorem. Okay, so if I write everything down, here you see the equation sort of in their full glory with all the non-local terms sprinkled all over the place, right? So these derivatives can be computed. I told you that they can be, and here they are. That's why I wanted. The other ones are easy to compute, but these non-local ones that depend on that I couldn't even write them. I wrote G index A, and I had to take a derivative relative to A, etc. No, here they are, explicitly written down. Now, you can do the same thing for more, right? So you have trees, right? Previously I had only one guy. Now this is fixed, this is a fixed rod, there's another fixed rod, here I have charge. So I'm not telling you that all of them have the same charge, not at all. Exactly as before. You can have various charges and various everything. And then you can build on it. And that is essentially you would like to do the same thing over again. Well, you can do it. 50 minutes, you can do it. What you have to do is, I give you the idea, and then I'm just going to show you the last slide. You have various groups acting here. Suddenly you have two groups, G1 and G2. And you have to take the semi-direct product of these two groups, which is non-abelian. And then you have to apply a kind of theory that I have done before for this non-abelian semi-direct product of two groups that are inherently non-abelian themselves. Right? They are rotation groups or Euclidean groups, things of that sort, symplectic groups. So you have an affine action that looks like this. You have a cocycle that is a cocycle of the semi-direct product. The relationships get much more complicated. there is work involved. You have to look at the Lagrange, and the Lagrange, you have many, many more variables. By the time the dust settles, what you get is equations of this type. And if you want to see them completely, these are Poisson brackets. If you really want to see them completely, I mean, here is for the strands, for a tree, level 2 tree. I mean, here are all the variables, who's measured relative to whom, right? And the Lagrangian is complicated. It depends on other variables. So these new variables, P, it's just, and if I have another tree, and more variables, they keep adding themselves. And then you have these two equations. But you can compute. And if you want n, you can compute n. Right? But the only point I'm making is it's explicit. Right? You give me the formula, you give me the Lagrangian, I sit down, I'll compute. And here are the equations. So, and to which you have to add the advected equation, which are much more, but these are the simple ones. These are things that are dragged along by the flow. So that you want to compute derivatives, here they are. I mean, finished. I'm going to stop. It's over. Thanks a lot.
This is the question?
Yeah. What's
Sure.
the conclusion for the strands themselves? I mean, what is
The conclusion, the conclusion is find the equations. We didn't know what the equations were.
Yeah, but once you have solutions, you said that you have some solutions. So
I didn't say I have solutions. I said I have equations.
how this
So these things now, I tell you why we did this. Because now you can apply variational integrators to simulate it. So there are methods in numerics that can simulate these constraint variational principles. And so at this point, we can give to somebody like this, and in fact, we intend to do this. I have a candidate with whom I want to do this, somebody who knows numerics, to actually see the motion of the strands.
But what I don't understand, it is, this theory describes one strand,
Yes,
and the collection of strands that
I don't have collection strands. Just one strand, and
suspended,
I have just then, and then I have the trees.
suspended
That's it.
vacuum or
Suspended in vacuum. I don't have fluid around it. I have no dissipation around it. There's many issues that are missing.
okay. Yeah.
I'm not trying to hide it.
The theory of one strand
One strand
vacuum
with conformations on it, or trees.
and why should you never used Frenet tripod along this?
No, because that is what Kirchhoff did.
Ah,
But if you do this, it's perfectly okay.
it's natural.
Right. If you do this, you're going to end up mixing variables, Eulerian representation variables and convective variables. And my experience has been that if you do this, the situation becomes very complicated. You lose track of what you're doing. It's like when you do fluids. I mean, in fluids we have the discipline because they're used to. Right? You either look at the Euler equations, which are in spatial or Eulerian representation, or you look in Lagrangian representation.
Yeah.
You don't mix them.
You can.
You can. But then you have other problems to keep a baggage with you all along. And this is what Kirchhoff does. And it's very nice what Kirchhoff does. I mean, it's not a criticism. Except that if it's getting more complicated, then personally, I'm losing track. The other, I tell you also another thing that was one of the other motivations why we did it like this, is because, for example, when you want to express elasticity, right? I give you fluids. I can express them in material, in spatial, but I can also express them in body representation if I want to, right? It's not done, but you can do it. In elasticity, you cannot. There is no spatial representation unless the material is isotropic. And since this was elasticity, I wanted to stick rigorously, religiously to the convective representation.
So you suggest that this is the simplest?
This is the simplest I can get, unfortunately, I'm afraid of.
Okay. You would like to ask something? Or you,
It was the same answer.
the same
I would
question.
like to see some kind of solution.
Some kind of solutions, yes, so would I.
Okay.
But since I'm not a numerician, and you know, find a particular solution of this.
Thank you
try.
once more. If it's no questions.
Okay.